So welcome back everyone. Let's get started with week 4 discussion. So until now, that is up to week 3, you looked into like finding solutions to, I would say finding simpler solutions to the Navier-Stokes equation where, your dependent variable, which in principle was the velocity profile. For instance, like where you looked into the flow of a fluid that is flowing through a flowing with that is flowing due to due to a applied pressure gradient between two parallel plates, which you more commonly encountered as the plane Poiseuille flow. Is that you so basically what you saw is that your velocity profile, which was uz, it was just dependent on the transverse direction, which was y. Okay. And similarly, when you looked into the curvilinear coordinates, like solving for the velocity profile, when there is an applied pressure gradient between two stations in a long cylindrical pipe, you saw that the velocity profile, which was unidirectional in nature, so basically we call it as uz, and you saw that your uz is just a function of one independent variable, which was the radial direction in that case only. Okay, so so mathematically, it just all all these examples, for instance, like the Couette flow, the plane parabolic flow, or the Hagen-Poiseuille flow. These things just boils down to the fact that you just require to solve certain ODEs in order to derive the velocity profile subject to the given boundary conditions. Okay, so that's one common aspect that these examples actually hinges on. Okay. However, now what we will see from these class onwards until the next 2 or 3 classes is that we will look to solve for velocity profiles in which the velocity field that we are actually going to calculate, they are just not going to be dependent on only one independent variable. Rather, they will be dependent on more than one independent variable. Okay. So in the language of maths, what it actually signifies is that your governing equation, which was earlier, so if you remember the governing equations of all the cases that we discussed in the last classes, those were just ordinary differential equations. Now what we will see is that since your dependent variable is dependent on more than one independent variable, you will see that the governing equations are essentially PDEs, or partial differential equations. Okay. So so that's one of the prime difference that we will see now when we encounter velocity profiles which have dependence on more than one independent variable. For instance, what you saw in basically in this week's lecture series is that you looked into calculating the velocity profile for certain kinds of flows where your velocity field is dependent not only on the spatial variable but also on the temporal variable, or in case this is so those and these analyses are typically known as transient analysis. Okay. uh, for example, you might have looked into the case that when there is a plate, okay, and you basically have a coordinate system something like this, where this was like your x direction and this was like your y direction, and simply you had a fluid which is above this plate, which was typically at rest. Okay. So this is one classic example which I believe you have known it as the Stokes-Hurst problem, where you have a big chunk of fluid. So you can think like this fluid basically goes to infinity in the plus y direction. Okay. So the fluid, you can tell is that there is an infinite volume of fluid that is sitting at a top a planar plate. That is something that you can interpret this as. Okay. So what you saw is that initially this fluid was at rest, and then what you did is, so basically you use the fact that at t equal to 0, the plate which will the plate velocity, which we will call it as up, this was 0, meaning that there is nothing which can actually disturb the fluid. But what happened is that at the next time instance, that is when uh, t equal to 0 plus, meaning that at the very next time instance, when you actually turn your clock, you actually give the plate a prescribed velocity of, let's say, up naught in the z direction. here it would be in the x direction to be precise. So basically what you do is you kind of like move this plate towards plus x with some given velocity up0. Okay, where is up0 is just some constant and it's a known velocity. So what basically happens now is that the fluid, as I hope you can realize, that the fluid will also continue to move because the plate itself starts to move in the positive x direction. Okay, so that's actually that will happen, and then you use the fact that your velocity is actually bounded. So what you said is that your fluid velocity, which we will call it as u, which will now be, I believe you can understand that now, since you are turning on the velocity of the plate at the next time instance, the fluid velocity will essentially depend on you know, two things. One, the location that is perpendicular to the direction of motion of the plate. That is obvious because when you try to move the plate in the positive x direction, the fluid here will get displaced much quicker than the fluid basically here. So you can see that there is an inherent variation in the y in the y direction of the x component of velocity. Okay, but now apart from this variation, we will also encounter a transient variation because of the fact that initially the initial condition says that the plate was at rest typically. Okay, which means that your u will also be a function of time. Okay, so that's one kind of problem that you solved, which you most commonly call it as the Stokes first problem. Okay, that's the name with how it goes. And then you use some, so basically, since so for this problem you saw that your PDE just reduces to the fact that rho times del u del t is equal to mu times del square u by del y square. Typically that's the PDE, or if you just do a simple simplification, you will see that your velocity field, which is of course you are just going to have an x directional velocity field because the plate just moves in the x direction. So there is nothing which can actuate the fluid in the y and z direction. So that's the reason why we'll just encounter only the x direction velocity field. And you saw that the velocity profile was del u del t is equal to nu times del squared u by del y square, where this nu is the kinematic viscosity. Uh, so this nu is the kinematic viscosity, which is given as the ratio of the dynamic viscosity to its density. Okay, so this is typically the governing equation that you solved, and I hope you can now see that your independent variable, which is, sorry, the dependent variable, which is u, that is the x directional velocity of the fluid that is basically being created due to the motion of the plate. This actually depends on two independent variable, that is your y and t. Okay, I hope you realize that your plate is kind of like infinitely long in the x direction. That means you can think of the x solution as a fully developed solution. So you kind of can interpret that your velocities will not be a function of x, it will not be a function of z, because this is kind of a 2D problem that we are actually, I mean, so basically we are trying to solve this problem in a 2D system here. So there is not going to be any dependence on z. And keeping in mind that there is nothing which can actually actuate the fluid in the y direction, that is not possible. So we don't have a y component of velocity, meaning that v is essentially equal to 0. So this is something that you actually solve for. Okay, and then you use something. So basically now you can see that you require two boundary conditions because your equation is second order in the spatial variable. So what you did is you use the fact that you know that your, so basically your velocity profile at y equal to 0, that is when you are looking the velocity field at the plate. So you know that this is typically equal to the plate velocity, which is up0, and this is a known velocity that we have. And then you also use the fact that your u, when y tends to infinity for all time, this is so its magnitude is less than infinity, and this is a condition which we call it as the boundedness condition. That is that your velocity field cannot blow up when you go far away from the plate, and that is obvious, right? Because you have viscosity which will actually try to slow down the disturbances that gets propagated from this position to the plus plus y direction. Okay, so this condition, this is known as the boundedness condition. uh, Boundedness condition. Okay, and these are the two boundary conditions that you had when you actually tried to find out the solution to this PDE. Okay, I believe you can interpret that this is a PDE, okay, because it's, as I said, your dependent variable is actually dependent on two independent variable y and t, okay. Now you can interpret that since this equation is also a function of time, you also need something which is known as the initial condition. We call it as IC, or the initial condition, and the initial condition is rather straightforward because we said that at time t equal to 0, okay, the plate and the whole system was basically stationary, which means that your velocity, that is u, at for all x, or I would say, rather I would say u for all y, because y is on which u actually depends on, and at time t equal to 0, this is equal to 0, okay. So so basically this is what we saw, that this is these are the two boundary conditions, and this is the initial condition that we use in order to tackle this problem. And what you did is, if you paid a little bit of a attention when the solution of this problem was carried out, you actually saw that in this problem we don't, inherently have something known as, so basically we don't have a length scale and a defined time scale in this problem, okay. So we will look into why I have made this statement very shortly after this discussion. But because of this fact that in this problem I don't actually have a defined length scale and a defined time scale in this problem, although I can have an defined velocity scale. For instance, like I can say that my velocity, that my characteristic velocity is equal to my plate velocity. This is something that we will see why this is called as the characteristic velocity. But in this problem, at least we saw that we don't have a defined length scale and a defined time scale of the problem. For example, if I mean, just to give you an example, if I ask you that when I set the plate in motion at time t equal to 0 plus, the question that I can ask you is that what is the length from the plate in the fluid when we move towards the bulk fluid? What is this length up to which my disturbance can actually propagate in a given time t? Okay, this is something that we cannot answer a priori, although we can answer when we are actually solving this problem. Uh, this is something that we cannot exactly answer given the problem statement that we have at our disposal. And also we don't have the fact that how long will the disturbance take to propagate a distance L. This is the second question that we don't have a priori in our question, okay. Although we can answer them when we are trying to solve this problem, but a priori before solving this problem we don't actually have the answer to this question. So that's the reason why when you look into the solution of this problem, you use something known as a similarity approach, or it's called as a similarity variable approach, where if you recall, you define something known as the similarity variable, which I believe you denoted is as eta, and then you say that your eta is a function of both y and t, okay. So the non-existence of these two, the a defined length scale and a defined time scale actually motivates us to find similarity solution in this problem. And that's the reason actually why you use a similarity variable to actually solve for the velocity field in this problem. The idea again is the same. What your quest is that you define the similarity variable in such a way that it has both simultaneous dependence on y and t, and then when you substitute the similarity variable after defining the similarity variable, if you substitute them into your PDE, which is basically this, you actually end up getting an ODE which depends just on a function which is just a function of the similarity variable eta. Okay, so in other words, you basically get an ODE of f which is just dependent on eta, but you know that your eta is an explicit function. you know Basically this eta is an explicit function of y and t. That is something that that we use, okay. And as I said, the motivation for using the similarity variable is that you precisely don't have a defined length scale and a defined time scale in this analysis, okay. However, a slight modification of this problem is also something that you have witnessed in the lecture series, is that now instead of saying that your plate velocity is equal to a given velocity which is up0, so in the Stokes first problem, I hope you can realize that you use the flat fact that your plate velocity is equal to up0, and this is a constant. I mean it's a known constant, okay. Now there is also something which is known as the Stokes second problem, okay, which also you have witnessed in this lecture series, in this week's lecture series, is that in this case, instead of saying that your plate velocity is equal to a constant at time t equal to, I mean, instead of the plate velocity being a constant, what you say is that now the plate moves back and forth with some frequency basically. So what you say is that instead of specifying the plate velocity to be constant, you say that this is equal to some velocity with an amplitude a times cos omega t, or maybe I'll call it as t bar for obvious reasons which will be clear later on. Okay, so now I hope you can understand that instead of saying that the plate essentially move with a prescribed velocity in the x, you now say that the plate moves back and forth with a given velocity whose amplitude is equal to a and whose frequency is equal to omega. Okay, that is the difference that you encounter when you solve the Stokes second problem with respect to the Stokes first problem, where you just had a prescribed non-zero constant velocity in the x direction. Okay, so I hope qualitative difference that you can observe in the Stokes second problem is that in the Stokes first problem, you know that your fluid will just continue to move. Your fluid will just continue to move. Maybe I'll draw. Okay, your fluid will just continue to move in the x direction, to be precise. Okay, in the Stokes first problem, but in the Stokes second problem, I hope you can realize that now the fluid will also oscillate with back and forth, because the plate kind of oscillates with back and forth. Okay, so the velocity field, if you draw for the Stokes second problem, is going to be something like this. So there will be oscillations, and slowly these oscillations will die down, will basically go to oblivion. So this is one qualitative difference that you saw when you actually solve the Stokes second problem, because now you know that the plate kind of oscillates about its mean position with a given amplitude a and a given frequency omega. So because of the fact that the fluid is viscous, the fluid will also exhibit an oscillatory behavior in the Stokes second problem. And this very information actually changes the nature of the solution in the Stokes second problem. Okay, in the Stokes first problem, where you use the similarity variable, now because you have a defined time scale of your problem, for instance, you know that your plate basically oscillates with a frequency omega, which means you have a defined time scale which is omega inverse. At least you know that in omega inverse the disturbances are actually going to propagate inside the fluid. Okay, so this time scale, as we will formally define very shortly, this is known as the characteristic time scale of the problem. Okay, this is known as the characteristic time scale of the problem. Okay, so the difference that you witness with respect to the Stokes first problem is that in the Stokes second problem, because you have a given defined frequency that we impose on the oscillatory plate, you have a characteristic time scale in your problem, which you actually didn't had when you were actually solving the Stokes first problem. Now, since you have a characteristic time scale and you know that your problem is going to be oscillatory in nature, this actually changes, as I said, the solution to the PDE. Okay, and then one thing that you have used is that you have assumed that your solution, that is your velocity field, which is going to be a function of y and t, this is going to be some real part of u hat of y e power I omega t bar. So this t bar is actually so for obvious reasons, as it will be clear very shortly, I will denote all the dimensional variables with t bar basically. Okay, where barred quantities these barred quantities are dimensional, meaning that they have actual dimensions in the analysis. Okay, so I hope you can realize that just by imposing a frequency to the plate, the nature of the PD has changed. See, the original PD is always the same, but the solution that you assume in order to solve the PD, that has changed basically, which will then change the solution that you are actually going to get after solving the PD. Because I hope you realize that the PD that we are actually trying to solve, this is still the same, because it is just del u del t equal to nu times del squared u by del y square. Okay, this is the same PD that we are solving, but the solution that we are assuming in order to solve the problem, this has changed, which will then change. Uh, I mean the form of the solution has changed, which will then actually change the original solution that we'll get when we solve this PD. Okay, so this is the classic hallmark of partial differential equation. is that even if you have the same PDE, it is the physical paradigm that dictates the nature of the solution that you will get once you solve the PDE. Okay. Uh, I won't discuss much on PDEs because this is beyond the scope of this course. But you know, if you take a classic maths course, you will actually see that while ODEs, you know, the same kinds of ODEs is not sensitive to the boundary conditions and the physical nature of the problem. On the other hand, PDEs, the solution of PDEs are sensitive to the boundary conditions that you have and the physical paradigm on which you are actually trying to solve the PDE. Okay, so that's the difference that you saw. Okay, so that's the difference that you saw when you solve the Stokes second problem with respect to the Stokes first problem. Okay, so this is a quick recap of what you actually learned in the in this week lecture series, and we will in this interaction session we will build on from here onwards. Okay, so before proceeding into the next part, I will stop here for a couple of minutes, and maybe if you have any questions you can feel free to let me know. Okay, all right, so the thing that we are going to learn in the next maybe half an hour or 45 minutes is, I would say, this is a little bit of extra information that I'm going to give you, but this is going to help you a lot when, especially when you want to, you know, pursue fluid dynamics or fluid mechanics, in particular, you know, low Reynolds number fluids or some analytical work in your research. This technique is actually going to help you a lot, and that's the reason why I believe you know, spending around half an hour or 45 minutes of discussion is deemed important in this regard. Okay, again I say this is kind of an extra thing that I'm going to share with you guys, so this is not exactly there in your lecture series, but this will help you, as I said, in you know, solving your assignments, of course. That's one aspect, but the second is that it will immensely help you while you are, if you pursue, you know, analytical you know, strategies in your research basically. Okay, all right, so the idea is that, you remember we basically discussed two things in the Stokes first and second problem. We said that in the Stokes first problem we didn't have a characteristic length scale and a characteristic time scale that is defined in the physical picture, but in the Stokes second problem, since the plate was oscillating with nature, we had a characteristic, or we had an imposed time scale to be precise, in our problem. Okay, so then the question is, why are these known as characteristic time scale? Okay, or why are these called characteristic quantities? Okay, and the second is, if we define characteristic quantities, what we can do is we can do something known as non-dimensionalization. That is, uh, we can solve the same ODEs which were earlier dimensional by converting them into non-dimensional forms. Okay, and then, or the obvious question that you should ask me, that why are we doing this extra thing? Because we can easily get because if we have the governing equation, we can easily do you know, the arithmetic to basically get the solution. Then why are we actually trying to, you know, convert them into basically why are we doing an additional step which looks, you know, unclear as of now, and then converting them into a non-dimensional version and then solving for it. So the obvious question is, why are we doing this? Okay, my answer to this would be yes. In case of simpler, you know, analysis, solving dimensional equation helps because you don't have, you know, much of the dimensional variables in your disposal. But when you are doing, you know, an involved analysis where, you know, you have multiple, you know, variables, multiple physical quantities, I would say, at your end, solving dimensional problem doesn't give you much of a physical insights. Okay, rather we will see that in fact in this course only we will see that instead of, you know, defining dimensional quantities and solving, you know, for the variables, if we can have a non-dimensional counterpart to the dimensional equation, we can actually, you know, extract lots of, you know, physical insights from the governing equations and the solution. Okay, for example, one obvious example that I can think of is that if I change the fluid, for instance, let's say I'm solving for a velocity field of a fluid that is flowing through a rectangular duct. Okay, in one case I'm considering that my fluid is, let's say, water. Okay, and then you basically solve for the velocity profile that you get when you are actually solving for the fluid inside, solving for the flow field inside the duct. The second instance, I would say that, okay, so now instead of instead of solving for water, let us now solve this for glycerin. Okay, and then the solution to the velocity field that you get while solving for water will contains all the variables which are subject to just water only. For instance, it will have density, it will have viscosity. Okay, and then when you are solving for some other fluid for some other given condition, you then again need to change your rho and mu, which will then change the ultimate velocity field which you are getting. Okay, but if you kind of solve this problem non-dimensionally, you actually don't need to worry about those physical quantities, because you will encounter something known as non-dimensional number. For instance, if you solve for a flow of fluid inside the duct, you may encounter something known as the Reynolds number. Okay, so for different Reynolds number, that you can then, just by changing the value of Reynolds number, you so basically what so my point is that you will get your velocity profile as a function of Reynolds number times times some non-dimensional variables that will pop up in your analysis. But then the added advantage is that I don't need to say that this velocity profile is just subject to one special kind of fluid, and that the velocity profile will change if I change the fluid, because all I care about is that my velocity profile is just a function of a non-dimensional quantity, and I can have multiple values of the velocity profile just by changing the non-dimensional quantity. Okay, so that makes my analysis generic, which was not the case when I was trying to solve this using dimensional quantities. Basically, that is one advantage that we get when we are actually trying to derive analytical solutions uh, for some complicated problem which involves lot of variables subject to the physical conditions that we had. Okay, that is that so that aids us in order to, or that motivates us, I would say, in order to pursue non-dimensional versions of the same dimensional equation. Okay, so the second thing is that's one advantage. The second advantage is that I can now look into the physics of the problem, and then can argue that how my problem, or basically how my solution, is going to span in a given in a given time or in a given space, meaning that I can tell that, okay, if I am now solving, let's say I'm solving the Stokes second problem, and then I say that, okay, it has been, so the fluid is being disturbed by a given by a given plate velocity which is having a amplitude a and a frequency omega. Okay, then for any fluid I can then argue that up to what distance from the plate will the effect of the disturbance propagate. Okay, and that distance, or that thing that I'll calculate, that is not just a function of a given fluid, but it's kind of a generic thing that we can get because we are using non-dimensional variables in our analysis. Okay, so 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 the ultimate key takeaway is that we can make things generic when we actually solve a equation non-dimensionally. And I believe that is one motivation that should propel us to study a little bit of non-dimensional analysis that we will do in the next, as I said, in the next half an hour to 45 minutes. And thereafter we will start off with finding a solution of something which is known as an oscillatory pressure driven flow inside a inside a cylindrical pipe, the dimensional version of which you have already solved in the week's discussion. But we will now try to solve that using a non-dimensional approach in our in our discussion. Okay, and then we will see that the answer that we will get, I may not be able to finish the answer by today, but at least in the next session we will see that the answer that you get of the non-dimensional version, if you then convert it back to the dimensional version, you will exactly get the same answer. Okay, all right, so any questions until this point? Okay, if not, then let's get started. So in order to understand non-dimensionalization of the equations, you must first understand something which is known as the scaling analysis. Okay, So as the name suggests, scaling analysis means whatever the variables that we have, we will try to pick some variables. If we divide the dimensional variables with those variables, that will give us correct non-dimensional variables. Okay, I emphasize on the word correct because we cannot just naively go ahead and scale any variables with incorrect characteristic variables, and that will not capture the physics of the problem. Okay, so we will see very shortly that it is very crucial to choose the correct characteristic variable uh, if we are performing a scaling analysis. Okay, so as I said, as the name suggests, we will now look into, so I'll maybe write it down. So we'll now look into characteristic variables uh, that can scale the dimensional variables in our analysis. So this might not be clear to you at this point, but I'll show you by a couple of examples, and then things will be much clearer to you later on. Okay, so then so let's first look at the scale for velocity. Okay, and this will make things very clear. Okay, so scale, so the first example that we will see is choosing a scale for velocity, or what precisely is characteristic velocity. Okay, so for this, let's take a prototypical example of a fluid that is flowing through maybe a cylindrical pipe, a fully developed flow through a cylindrical pipe. That's something that you guys have encountered frequently, and maybe we will consider this, that the flow is fully developed in this section of the pipe. You can think of like pipe of, you can think of the pipe being going, which is very long, meaning that the flow is basically fully developed in between these two sections. That is something that you can interpret. And then if you draw the velocity profile, you know that your velocity profile is parabolic. This is a well established velocity profile that you know. And you know that your velocity profile uj, where z is basically this direction, is just going to be a function of r, and this is going to be 1 upon 4 mu times dp dz times r square minus small r square, where this r is nothing but the radius of the pipe and small r is the radial direction in the cylindrical coordinate. Okay, so this is something that we have derived in the previous weeks, and I believe you are familiar with this so far. Okay, so then if someone asks me that can I now define a non-dimensional, so I hope you realize that this uj that I have written, this is a dimensional variable. Okay, so so unless I mention otherwise, I shall denote all my dimensional variables as dash quantities. Okay, so that means that my uj is going to be dash because this is a dimensional variable, and so is r dash and this small r dash. Okay, meaning that this is precisely a dimensional quantity that we have, which actually has dimensions. Okay, now if you ask me that can I choose a characteristic velocity such that if I divide this dimensional velocity with the characteristic velocity, I will get a non-dimensional velocity field, which is just going to be uj, a function of r, where z and r and u are now non-dimensional quantities. Okay, so then what I can do at this point, if you ask me to find out the non-dimensional variable, is that I can tell that yes, I can choose a characteristic velocity. This is called as a characteristic velocity field. We generally call it as UC. I can tell that this can be equal to the maximum of uj prime of r prime, or average of uj prime or r prime of r prime basically. Which means given this velocity field, I can choose, okay, the characteristic variable to be the maximum or the average. Whatever you choose, this is completely up to the user. This is completely up to us basically. Okay. For example, my characteristic velocity, if I choose my maximum, is going to be, so if I so this velocity is going to be maximum at here, meaning that this r is going to be equal to 0. I know that my characteristic velocity is then going to be 1 upon 4 mu dp dz times r square. This is what is going to be my characteristic velocity. Okay. So then what I can do is I can then define a non-dimensional velocity uz of r, which is then going to be the dimensional velocity uz divided by the characteristic velocity. And now we can, very nicely find out what is uz of r in this case. Okay. For example, if you look, okay, maybe I call it as equation 2 and this is equation 1. Okay. So what I'll do is if you take equation 1, okay, and if you take capital R square common, so what you will see is you will see uz prime is equal to minus of 1 by 4 mu dp dz r square 1 minus of r dash squared by r squared. Okay. And then I say that this is going to be my characteristic velocity, right? Because I have chosen my characteristic velocity as the maximum velocity precisely. So this is going to be my uc, and then what I can do is I can write this as uj prime by uc is equal to 1 minus of r prime squared by r squared. Okay. Now you can very nicely see that this quantity uj prime by uc, this is a non-dimensional quantity because the dimension of uc and the dimension of uj prime is going to be the same, which means I can then write this as some uj of r, because I can also equivalently define a non-dimensional length scale which is going to be r, and then this is going to be r by capital R. Okay. And then you can say that you can argue with the same logic that this capital R happens to be my characteristic length of my problem, of the problem, which we generally call it as LC. Okay. And of course this is R dash. So then I can then write the non-dimensional version of this equation 1 as uj equal to 1 minus of r square. That's it. That's just becomes the non-dimensional version of equation 1. Okay. So this is your non-dimensional form or version of equation 1. Okay. See, as I told you, now you will see obvious advantage of using this equation instead of using this equation. The number one is that if you change the pressure gradient, the magnitude of this quantity will change. On the other hand, if you change mu, the magnitude of this quantity will change. But all of this doesn't bother us when we use this form, this non-dimensional form in our equation, because here we don't actually need to think about, okay, if I change dp dz, how will this equation change? This is something that I don't need to think about because that is already embedded in this characteristic velocity uc. So at next what will happen is if I have a different fluid, my characteristic velocity will change because okay, I know that mu will change now because the viscosity might change. Let's say we are going from water to glycerin, this mu might change, so this characteristic velocity will change, but the final form of the non-dimensional version of your equation will not change because now we have written the quantities in a non-dimensional way. That means we have used all the scales correctly in order to capture the essential physics that needs to be captured if we use this form of the non-dimensional version. So if you then solve for whatever the quantities that you're actually trying to solve for using this non-dimensional form, I don't so my point is this form is generic and I don't actually need to think, okay, what will happen if I change my fluid, or what will happen if I change my pressure gradient, or things like that. Okay, so that is one advantage of using non-dimensional versions in our equation. Okay, so things will be more clear if we when we go ahead, and I hope I'll be able to justify you that using non-dimensional variables actually helps in our analysis. Okay. All right. So then we encountered two things. Number one, how to choose characteristic variables. For instance, I said that, so for example, you can also choose your average velocity to be the characteristic velocity here. Okay. Then the average velocity, you know that this is going to be, so for pipe flow, you know that the average velocity is half of the maximum velocity, which means this becomes 1 upon 8 mu times dpgz r square. So to be your characteristic velocity, if you choose your characteristic velocity as the average of this uj prime basically. Now, what you choose, that is completely up to you, but you need to make sure that you essentially capture the physics correctly of your problem. Okay. All right. So then we looked into the scale for velocity, and in doing so, we also looked into the scale for length. For instance, this now you can say that your LC, as I said, this is known as the characteristic length. And here, my characteristic length just happens to be the radius of the pipe, which is r. Because I can always define a non-dimensional r, that is a non-dimensional radius, as my dimensional radius divided by LC, where this dimensional radius by LC, and in this case, my LC happened to be equal to r, which is just the radius of the pipe. Okay. So that's the second thing that you learn, that how do we choose characteristic length in a given problem. Okay. I hope you realize that here the radius of the pipe, this capital R, came out to be the characteristic length. But if someone argue that okay, instead of choosing this capital R, instead of choosing this capital R, what if I choose the span of the pipe as, for instance, if I choose this L, this capital L as my characteristic length instead of choosing. So my question is, what will happen if I choose this L as my characteristic length instead of choosing this capital R as my characteristic length? I would say that would be an incorrect choice of the characteristic variable. The reason is, see, the velocity profile that we have, this actually varies when we move along the R direction in this scenario. Okay, the velocity profile is kind of an invariant when we move along the x direction, to be precise. So we need to choose that length on which we are seeing an appreciable change of the variable of interest typically. Okay, so that's the second, or I would say is the third aspects of choosing characteristic variable, is that you must choose the variable, or you must choose the length scale in such a way such that you see an appreciable change in the quantity of interest. For instance, here the velocity is the quantity of interest, and I have chosen my length scale, the characteristic length scale, to be the radius of the pipe, because I know that along the radius my velocity is going to vary typically. But along the length of the pipe, I know that my velocity is just an invariant, because this is a fully developed flow, which means that there is no point to choose this capital L as my characteristic length scale, typically because if I choose that, I cannot see a change in the velocity profile. Okay, so choosing L, so I'll write here, uh, so maybe I'll write down here that choosing L, which is the length of the pipe, instead of R, which is the radius of the pipe, is not a correct choice of characteristic length. The reason is because along L, or maybe I'd say along X, the flow field does not change. Okay, so this is also one aspect, that you cannot just go ahead and naively choose a characteristic variable. You must choose the characteristic variable, for instance the primitive variable, for example like length, time, and things like that, such a way that there should be an appreciable change in the quantity of interest that you are actually trying to evaluate. Okay, all right, so that's the second part, that is the choosing the scale for length. Let's look into some more scales. For instance, let's look into the scale for stresses. Okay, okay, so here you need to understand certain things. For example, if I have a quantity, let's say I have a dimensional quantity, okay, which precisely scale says A. So this symbol that we will use, so we'll use very, you know, so this symbol we'll use very often. This symbol is known as scale says. That means, you know what this actually means? This means that when I say that for instance, when I say that okay, maybe I should call it as maybe some, okay, it's okay, maybe I'll call it as x prime, doesn't matter. So what actually means is that if I say that a variable scales as a certain variable, it means that this variable is not exactly equal to this a, but it is kind of a ballpark figure of a. Basically it's kind of, it's so the magnitude of x is somehow in the close vicinity of the magnitude of the variable a, or in fact the magnitude of the constant a that we choose as the characteristic variable. Okay, so this is what actually the scale as quantity means. It is precisely, it means that it is not exactly equal to a, but it is kind of a ballpark figure of the magnitude of a. That is what actually the quantity scale says implies. Okay, so what I mean to say that if I have a quantity x prime which scales as a, and let's say I have a quantity y prime which scales as b, then dy prime by dx prime, this will scale as b by a. Okay, so this is something that you need to understand in while you try to figure out what the scales of stresses would be. Okay, all right, so if this is clear, then I can, we can actually find out what the scales of stresses would be. Okay, for example, I can write, let's say we are considering a planar, co-wave flow, then the stress that I will have is nothing but uxy, which is equal to mu times del u by del y. And again I say, because this is dimensional, I will call all the quantities as dash quantities. Okay, then what I will say is that if my dimensional u scales as uc, where uc is the characteristic velocity we have already seen. For example, if this is a pipe flow, the characteristic velocity is the maximum of the, or the average of the velocity profile. For example, if this is a quid flow, you can choose your characteristic velocity as the velocity of the plate. Okay, that's completely up to you. I hope you have realized this until this point. Okay, so this uc is the characteristic velocity that we already know, and I can then say that my y prime is nothing but the characteristic length LC. Again, this is something that we have extensively discussed on. For instance, if we have a quid flow, the length is going to be the gap between the plates. If I have a Hagen-Poiseuille flow, the characteristic length is going to be the radius of the pipe. Okay, where this LC is the characteristic length, and then I can say that I can have a characteristic variable for stress, which we will call it as tau c. This will basically scale as mu times uc by lc. Okay, so this is typically the scale for stress. Okay, for example, if we look into the Hagen-Poiseuille problem, I can tell that my tau c is going to be mu times u max by r. This is precisely going to be my characteristic stress. Okay, I, because we know that uc was equal to umax in that case, and lc is going to be the radius of the pipe. Okay, all right, so this is how you choose scales for stresses based on the choices that you have already made on the primitive variables, for instance like the length, uh, the velocity and things like that. Okay, all right, then comes one more important uh, scale, which is the scale for time, for the time variable. Okay, so scale for time. So we can define this as we seek. So basically the idea of choosing a scale for time is that we seek the time span, okay, over which there is a considerable change in the variables of interest. Okay, so for example, what it means is, let's just consider a very simple example. Okay, if there is a bird that is, let's say we are considering a bird that is flowing through air uh, by flapping its wings. So let's say the bird basically, it moves through air or it glides through air by flapping its wings. Okay, where the frequency of at which the bird flaps its wings, let's say we are considering it as omega. Okay, then if I want to evaluate what is the velocity field that this bird or I would say what is the disturbance that this bird propagates to the quiescent air is the disturbance velocity field. And for that, if I want to choose a defined time scale, or if I want to choose a time scale, one option that I have is that I can choose my characteristic time as omega inverse. Because over an order omega inverse, I know that the bird is going to again change the orientation of its flaps, which means that at least up to an order of 1 by omega inverse, or up to a time span of 1 by omega inverse, I will know that the bird had already propagated its disturbance into the surrounding fluid medium. Okay, so this is one option. I'm not telling that it is the option that I have of choosing the characteristic time variable, but this is one option which I have, because I already know that at least up to an order 1 by omega inverse, my disturbance is going to get propagated from in the fluid medium. Okay, so this already given time scale. So for example, if I want to solve for the velocity field in this problem, omega is going to be known to us, right? Which means that omega inverse is a known quantity. So this time scale where we actually get from the known quantity, this is actually known as the imposed time scale. Okay, for example, if you pay some attention to the Stokes second problem, which we discussed here, you know that the fluid is going to get disturbed because the plate moves back and forth with frequency omega, which means here also we have a defined imposed time scale which is of the order of omega inverse, on which I know that the disturbance is going to get propagated from the plate to the bulk fluid. Okay, so that's an imposed time scale that we have in our problem. Okay, or it is sometimes also, so sometimes it is also, so this imposed time scale, this is also sometimes known as an inherent time scale of the problem. Okay, uh, this is also sometimes known as inherent time scale of the problem. Okay, but this is not only the time scale, as I said, that can arise, because we can also have something which is known as an advection time scale. So basically we have two other time scales that can have typically. One is also called as the advection time scale. Okay, and maybe if I write down the Navier-Stokes equation, these advection time scale will be clear to you. For instance, if I write down, let's say I just write down the x direction Navier-Stokes equation. Okay, I can then write it as something like this, where remember these dash quantities are just dimensional quantities. That's what I have written here. So this is u dash by del u dash by del x plus v dash by del v dash, sorry, this is going to be u del u dash by del y, and then this is going to be equal to minus del p prime by del x prime plus mu times del squared u prime by del x prime squared plus del squared u prime by del y prime squared. Okay, so this is just, so think about, like, I am writing the Navier-Stokes equation in the x direction for this particular problem. Okay, considering that it's a 2D problem that we are actually trying to solve for, you know maybe I can call this axis as my x and this axis as my y, and I'm just trying to solve this in a 2D domain. Okay, then I can write down the Navier-Stokes equation something like this. I beg your pardon, this is going to be t. It's going to be t prime. Okay, and then in addition to having a imposed time scale, I can also have an advection time scale, for which I will write down this term del u prime by del t prime, and I can tell that this term basically scales as some uc by tc. Okay, because I already told you that if a variable x scales as a, if a variable y scales as b, then dy dx will scale as basically b by a. That's what I have used here. Okay, and then I can then write the scale for this term, which is this particular term, as u prime del u prime by del x prime to scale as uc squared, okay, by lc. Okay, I hope this is clear. See this term, I hope this is clear. How did I write this from this? Because I know that this term will scale as uc by lc, where uc is the characteristic velocity. Let's say we know the characteristic velocity in this problem. And this term would basically scale as uc, which means the entire term would scale as uc square by lc. Okay. And then if I then tell you that I have an advection time scale for the problem, then this uc by tc, which is the order of magnitude of this term, this is precisely going to be the order of magnitude of this term, which is u prime del u prime by del x prime, which is going to be uc squared by lc. Okay. And then what you can do is you can calculate this tc here, and then you can see that your tc is just going to be lc by uc. Okay. So for example, in the pipe flow problem, I can call this lc as my r, and uc is going to be my u max. Okay. Then this time scale, if you use this time scale in your problem, this is actually known as the advection time scale. Okay. You can think of this time scale as like, okay, if inertia is dominant in your problem, okay, then the time scale on which the disturbance can get propagated is dictated by the advection time scale. Okay, that is something that you can physically interpret this advection time scale as. Okay, you can also, in the same spirit, you can also have you can also have something known as the diffusion time scale. Okay, when you say that, okay, now equating the order of magnitude of this term to this term, if you equate the order of magnitude of this term, that is the temporal term, with this particular term, you basically get the diffusion time scale. So let's do it. Maybe what you can do is you can tell that, okay, del u prime by del t prime is roughly of the same order of mu times del squared u prime by del x prime squared. And then you know that del u prime by del t prime actually scales as uc by tc, and this scales as mu times uc by lc squared. And then you can actually get a time scale from this problem. Okay, so there is a row here. Okay, I think I missed the row, because remember there is a row here. So the row would not be a problem, because here the row would get cancelled out, because we are just comparing this term and this term. But if we compare this term with this term, then this row should be taken care of. Okay, so that's why there is a row, which means okay, which means there's a row here. And then I can tell that my tc here is going to be rho lc square by mu, and I can write this tc, or maybe I can rewrite this as lc square by mu by rho, and this becomes lc squared by mu. Okay, so this time scale, which is equal to lc squared by mu, this time scale is known as the diffusion time scale. Okay, so you can interpret it as like, if diffusion is present in your in your physical paradigm, then how how long will it take to impart or to propagate the disturbances just by diffusion only. Okay, that is given by the diffusion time scale, which, as you can see, is a property of the fluid, which is mu by rho divided and it contains the characteristic length lc in your problem. So you kind of encounter, so mainly in fluid dynamics we'll encounter only these three time scale, which is the imposed time scale that is given by the problem, the advection time scale, and the diffusion time scale. So quickly you can check one thing, that let's take the ratio let's take the ratio of the diffusion time scale to the advection time scale. So this is generally known as td. This is known as the diffusion time scale. This is generally called as ta, which is the advection time scale. Okay, so if I take the ratio, let's see what we'll get. So the diffusion time scale is, okay, it is lc squared by nu, and my advection time scale is lc by uc. Okay, so let's write it down. So maybe I'll get an lc cancelled here. So this is lc UC by nu, and then I will write it. So this nu I will write it as mu by rho. So this becomes rho times LC UC by mu. And if you pay a closer look, this is nothing but your Reynolds number corresponding to the characteristic lengths. So always remember that the ratio of the diffusion time scale to the advection time scale is given by the Reynolds number. Okay. So this ratio, this is nothing but your Reynolds number. So this means you can do a certain, so you can basically make a certain observation here. For example, if your Reynolds number is very large, this implies that your diffusion timescale is very much larger than your advection timescale, and this implies that your advection is a dominant mechanism. Okay, advection is dominant. See why this is the case? Because you know that, see, it is the lower time scale which will actually dictate the main change in the problem. Basically, if your Reynolds number is very much large, you know that advection actually overpowers the viscous terms, basically. Okay, or inertia overpowers viscosity. That's typically what we know, which means that my advection time scale is smaller than the diffusion time scale, which equivalently means that the disturbance that is going to be propagated is actually dictated by the advection time scale only, because the diffusion time scale is much larger than the advection time scale. So the change that will occur is going to be dictated by the advection time scale, when in the case when Reynolds number is very much greater than 1, or in the scenario, or equivalently the scenario when inertia forces dominate over the viscous forces. In other words, you can also say that when your Reynolds number is less than 1, you know that your diffusion time scale becomes very much less than your advection time scale, and in this scenario, your diffusion is dominant. Okay, so this is something that you need to understand in case of time scales, basically. So finally, I hope this is clear. And finally, there is the last scale, which we call it as the scale for pressure. And what I would suggest you to do is, so I'll give you a hint. There are actually two scales of pressure depending on the Reynolds number of the flow. Okay, pressure can actually scale as the viscous term. Pressure can also scale as the advection term. Okay, so what I will ask you to do is try to get the value of this PC, or the characteristic pressure, which is the scale for pressure, considering the two scenarios when inertia is dominant, as we did for the time scale analysis, or when the diffusion is dominant, to find out the two different scales for pressure. Okay, so this is something that I would encourage you to do. I will not do here, but I would ask you to do. And if there are any doubts, please let me know. I'll discuss in the next session. Okay. So what you can do at your end is try to figure out the two scales for pressure. Okay. All right. So this is something. So this is, I understand this is a bit of an extra information that I gave you. This has not been directly discussed in your lecture series, but the understanding of this is important, as I said, going forward, because one, you know how to basically non-dimensionalize things. Two, it gives, it makes things generic. That is something that you can always argue when you're using non-dimensional things. And in order to non-dimensionalize your variable, you need to choose your characteristic variable. And for choosing the characteristic variables, you will need to have a proper idea of the scaling analysis, how different variable scales in a given physical paradigm of interest. Okay. All right. So this is something that I want to discuss. I'll stop, and then I'll proceed with the problem that I propose to solve. Maybe I cannot finish the problem, but at least I can set up the problem, write down the governing equations and the non-Mamsell version of the governing equations by choosing the scales. But before that, I'll stop here for a couple of minutes, and please let me know if there are any doubts. Okay, please try to do this at your end. Try to get the two scales for pressure. And if not, if you feel any difficulty, please let me know in the discussion forum of the course, or let me know at any point, and I'll be happy to discuss them in the next discussion session. Okay, if there are no questions, let's now try to solve a problem, taking into account that we will use the non-dimensional versions and the idea of the scaling analysis that we have learned very recently. Okay, and this is a similar problem that we have solved. I believe you don't need introduction to this problem because you have already witnessed this in the lecture series. So what we are trying to solve is we are now looking to calculate the velocity field that is generated inside the cylindrical pipe by applying a pressure gradient which is oscillatory in nature. This kind of similar to the Stokes second problem, but in the Stokes second problem you saw that you had an unbounded domain. Here we have a bounded domain, meaning that we also have a defined and an imposed length scale in our problem. Okay, this is one way of distinguishing this problem with the Stokes second problem. The second thing, as I said, which was also earlier present in the Stokes second problem, is that you also have a defined time scale or an imposed time scale which is omega inverse. Okay, but always be careful that this doesn't mean that there is no diffusion time scale or adversarial time scale. These time scales are always there. It's just that which time scale basically dominates over the other is something that we need to do the analysis for. Okay, as a part of the analysis while solving the velocity profile, if we are trying to solve problems non-dimensionally. Okay, so as I said, that's all that I need to solve. And maybe I'll call here, I didn't write, maybe I'll call all the dimension variables just for continuity as barred quantities or dash quantities. That's why these are just dash. And uh, and yeah, okay. So so that's what we are going to solve here. As I said, so objective is, so I'll write down the objectives, what we actually need to do in this problem. So the objective is, first of all, identify the appropriate characteristic variables. The second thing is that derive non-dimensional governing equations and boundary conditions. Okay, and the third and the final objective, which I believe we may not finish it in this in today's discussion, is that obtain the velocity profile. Okay, but at least we will try to finish the first and the second objective. That is we'll start from the dimensional versions, and then try to solve for the non-dimensional and try to implement the characteristic scales in order to derive non-dimensional version of the dimensional governing equations. And obtaining the velocity profile is very similar to the one that we have already did. We will do that nevertheless, but first let's try out to get the appropriate characteristic variables, because this will then serve as an exercise of whatever learnings that we have done in the past half an hour or 45 minutes. Okay, and then using the characteristic variables to derive the non-dimensional governing equations. Okay, all right, so that's it. So let's get started. So I believe you all know the drill. So we should typically start off from the assumptions. But as I said, I'll so we have been doing this repeatedly. So I'll not write down the assumptions, but you all know what the assumptions will be for this case. For instance, it is going to be a fully developed flow, and there is no body forces and things like that. The flow is unidirectional, which means that there is not going to be ur and u theta component of velocity. It is going to be fully developed, and things like that. Okay, for so these are just the assumptions, the standard assumptions that we'll use. Okay, so I'm just not writing them down, but I believe at this point of time you are well equipped with how to write down the assumptions and invoking them into the main governing equations. Okay, so what I'll do is I'll start off from the simplified Z. So I hope you understand that the flow is unidirectional and is along the Z, because see, this is a cylinder, so we had been doing this repeatedly, that the flow is going to be along the Z direction only. Okay, see, had this pressure gradient be uniform, we know that the profile is going to be parabolic in nature. But just because of the fact that there is an oscillatory pressure gradient, the fluid will also oscillate back and forth. For instance, at one instant of time, your profile can be like this. At the next time instant, your profile can also be like this, because of the fact that your pressure gradient will continuously oscillate back and forth. Okay, that makes the problem a problem which is just not that makes the velocity profile, I should say, just not a variable in space but also a variable in time, and this is how it differs from the classical Hagen-Poiseuille flow that we had been deriving for. Okay, all right, so we'll write down the simplified Z momentum equation, and this is how it goes. So this is rho times del uj prime by del t, and this is equal to minus del pj prime by del j prime, where I reiterate that all the prime quantities are dimensional quantities, plus mu by r prime del r prime of r prime del uj prime by del r prime. Okay, so that's the simplified Z momentum equation, and I know that this quantity, this dp del p by del z, I know that this is equal to some g naught of cos omega t prime, that is typically given in your problem. Okay, that your dp g z or del p del z, because you know that your del p del z can either be constant, but here it is at max a function of time because this is oscillatory in nature, and that's the reason why this is equal to g naught cos omega t prime. Okay, so I'll write it down. So this is equal to rho times del uj prime by del t prime, and this is equal to g naught cos omega t prime plus mu by r prime del r prime of r prime times del uj prime by del r prime, where this g naught is the amplitude, is basically the amplitude of oscillation. This is the amplitude, and this omega, as you can see, is nothing but the frequency. Okay, so maybe I'll name this equation, maybe I'll name this as equation 1, and this is your governing equation that you are basically going to solve for. Okay, then let's write down the boundary conditions as well. So so the boundary condition is that I know that at uj at r prime equal to capital R, that is at the periphery of the pipe, for all time I know that this is equal to 0. This is because of the no slip boundary condition. And the second boundary condition is I will tell that the magnitude of uj basically remains bounded. So this is less than infinity for all r prime, meaning that so the meaning of this is that the velocity field is bounded. So actually this the second boundary condition, this is also known as, this is sometimes known as boundedness conditions, boundedness boundary condition, this is sometimes called as that. Okay, so this is known as a boundedness condition. It just says, see, the physically what it says is that your velocity field cannot blow up, basically that's what it essentially says. Okay, all right, so that's it. So this is the equation that we need to solve for, and these are the two boundary conditions that we should use. Typically I'll call it as 1a and 1b. Okay, but remember, I promised you and I said that we will be solving this using a non-dimensional variables, and because of that, the first step of, or the first objective that we should do is choosing the characteristic variables. Okay, let's see what variables are already there in a problem, and in that way we will choose the characteristic variables. For example, I can say that my characteristic time scale, so I can choose my characteristic time scale Tc as omega inverse. That is typically because I know that there is an imposed time scale in this problem, as we have discussed, as we have been discussing repeatedly, which is equal to omega inverse. And within this time scale, because I know that there aren't any mechanism which can act, which is actually actuating the flow, my changes or the disturbances that will be propagated is going to be dictated by this omega inverse time scale, which is the inherent time scale of the problem. Okay, so so that's the reason why I will choose my characteristic time scale Tc as my omega inverse. In the same spirit, I can also choose my characteristic length scale Lc as r, which is the radius of the pipe. Okay, so this is the inherent time scale that I have chosen. And this is the inherent length scale, because this is already there in the problem. Okay, or this is, maybe I'll call it as the length scale only, because we generally have only one scale for length. Or no, maybe here we also have the pipe length as the length scale, but we cannot choose that because, as I said, basically that is where we don't see a change in the velocity profile. Okay, so this is the correct length scale, I should say, and this is just the length scale. Okay, let's just call it as the length scale. Okay, and actually I will not call it as an inherent time scale. Maybe the correct word is calling it as the imposed time scale, because this is what is actually causing the fluid to move. So I'll basically call it as the imposed time scale only. Okay, that's it. Now, these are the two scales. I hope you realize that these are the two scales that we already have in our problem. I hope you also realize that in this problem, we don't have a given velocity scale. That's the reason is we don't know the velocity profile as of now. So if we don't know the velocity profile, we cannot just choose a given velocity as my characteristic velocity. So what we'll do is we will try to derive the velocity scale from the given, imposed time scale and the length scale basically. So for that, what we'll do is, see, I know that whatever is the change in velocity field that will occur, it is dictated by this pressure gradient, which means I can then say that in order to get the magnitude of the velocity scale, what I will say is that my order of magnitude of the pressure gradient is going to be order of magnitude of this term. Okay, and this is going to give me a velocity scale. Why? I will show you just now. So what I will say is that my order of magnitude of minus of d t prime by dz prime is going to be of the same order of magnitude of mu by r prime del r prime of r prime del uj prime by del r prime. Okay, this is something that I have argued. I am just saying, see, the reason is very simple. I know that the flow field is being generated by an oscillatory pressure gradient, which means whatever the disturbance that or whatever or what with whatever the velocity the fluid will move, because of this oscillatory pressure gradient, is going to be dictated by this, by the order of magnitude of dp dz only, because this is what is actually causing a change in the velocity field. Okay, and that's the only reason why I'm saying that, okay, the order of magnitude of this term has to be equal to the order of magnitude of the viscous term precisely. Now I know that the order of magnitude of dp dz is going to be g naught. Why? Because I know that dp dz has got a value of g naught times cos omega t, and I know that this cos omega t is just going to give me values between -1 and 1, which means that the ballpark figure of dp prime by dz prime is going to be just g naught, which is just going to be the amplitude of oscillations. Okay, and this g naught is known to us. Remember, this g naught, which is the amplitude of oscillations, this is a known quantity, which means that it actually hints us that we can get a velocity scale out of this known quantity, because I know that the velocity of the fluid is dictated by this amplitude g naught. If so, for example, actually it is also dictated by the frequency, but I know that cos omega t, whatever be the value of omega, is just going to be -1 and 1, which means the order of magnitude of dp by dz, which is the pressure gradient, is going to be dictated by its amplitude g naught. And that's the reason why I say that this this order of magnitude of minus dp by dz prime is going to be just g naught. And then I say that this scale says, so if you basically do the analysis here, that is you just take out the characteristic variables, you will see that this basically goes as mu times uc by lc squared. Okay, and you know that this is mu, uc is not known, but lc is going to be the pipe radius, which means that I can now have an expression for uc, which is the characteristic velocity, as g naught times rc squared by mu. Okay, so this is typically the characteristic velocity of the problem. So this is, so again I say this is not unique. For example, you can also do an order of magnitude of maybe you can do an order of magnitude of this term and this term, okay, and get a characteristic velocity. But I would say the more appropriate characteristic velocity is going to be, because this is a viscosity dominated flow, you don't actually have the true inertia term because this is just the transient term. The more correct characteristic velocity would be when you compare this term with basically equal to this term, because this is what actually is going to be dictated. I mean, this is what the physics says in this problem. That's one argument of choosing why I have compared the order of magnitude of this term and this term. The second thing is why we are doing this. We are doing this because in this problem we don't actually have imposed characteristic velocity in this uh, in this exercise. For example, things would have been very easier for us. Let's say you are calling that, let's say I'm imposing a shear flow here, okay? By some means I'm imposing a shear flow in addition to this pressure gradient. And let's say the shear flow has got a magnitude of some u naught times, let's say some okay, maybe some er prime, whatever it is, okay? You cannot generate ideally a shear flow here, but I am saying that by some means I'm imposing some background flow in this problem. Then you can argue that, okay, in this case I can choose the characteristic velocity to be the magnitude of the imposed background flow. Okay, for example, you can impose a parabolic flow here. This is one easy thing, because this pipe is cylindrical. You can easily impose a additional parabolic flow in addition to the flow that is being generated by this pressure gradient. And then you can choose, then basically you have two velocity scales in your problem. One, the velocity scale that is being generated by this oscillatory pressure gradient, and the second, you can have a velocity scale that is being generated from this here from this background flow. Now what to choose is on your hand, and equivalently you will get a different form of the non-dimensional equation, but the physics will always remain the same regardless of what velocity scale you choose, yeah, if you encounter two multiple scales. But here, since we don't have any other velocity scale, the only way I can choose a velocity scale is that I can basically get it from the imposed pressure gradient, because this is the only mechanism which is which is basically causing the fluid to move. Okay, that's the idea. I hope I hope this is clear, and I hope I am able to convince you why this is the velocity scale that we have chosen in this analysis. Okay, that's it. So we have the velocity scale, and okay, now I think that's it. We have the scale for length, we have the scale for time, we have the scale for velocity, and these are the only three variables that we have. So then so what we can now do is define the non-dimensional variables. Okay, define the non-dimensional variables, because ultimately we need to get a non-dimensional equation out of the dimensional equation. Okay, and that's the reason why we are choosing these scales. Always remember that. Okay, so I can now define a non-dimensional velocity. We'll call it as uj. So anything which don't have this dash, okay, I was calling it as bar, sorry, these are actually dashes. Okay, so I'm just denoting this dimensional quantities with dash. Basically that's the thing. Maybe I mistakenly wrote barred somewhere. These are not barred, these are dash basically. Sorry for the confusion. Where did I put where did I wrote? I don't know. Okay, maybe I hope you get the point. Okay, so any dash quantity, these are dimensional, and anything without it, these are all non-dimensional quantities. So I can define a non-dimensional velocity as a dimensional velocity divided by the characteristic velocity, which is uc. Okay, and I know what is uc. Uc is just g naught r squared by mu. That is my characteristic velocity. Okay, I can then define my characteristic radius as the dimensional radius by r. I can then define my characteristic, or sorry, I can now define my non-dimensional time as the dimensional time by characteristic time, and this characteristic time is omega inverse, so this just becomes omega t prime. Okay, all right, so then let's invoke these non-dimensional variables into the governing equation basically here. So I'll write down, so I'll now transform this governing equation by replacing all these dimensional quantities with their non-dimensional counterparts. Okay, so let's look the first term, which is rho times del u z prime by del t prime. Okay, so let's see this, rho times del u z prime by del t prime. So this term would be rho times, I will replace del z prime as, so this del z prime, this can be written as uc times uz. So this would be uz times uc by del tc times t basically. And since the characteristic variables are just constant, so they will basically come out of the differential. So this becomes rho times uc by tc, and then I can write this as del uz by del t, and I know tc is omega inverse. I am not substituting uc yet, and things will be clear why I have not substituted them. Okay, so this quantity rho times del u z primes by del t prime, this basically becomes equal to rho times omega, because tc is omega inverse, times uc by times del uz by del t. Okay, so that's it. That's what, the first term basically looks like when you write them in terms of the characteristic and the non-dimensional variables. Okay, then let's look into the other term. The other term is simple. I have the pressure gradient, which is, so the pressure gradient is g naught cos omega t, and this, the non-dimensional version would be just g naught, I mean, the version with the characteristic variable should be g naught times cos c. This is t prime, and I know that t prime is going to be omega inverse. So this is, so basically, so this t prime is going to be omega inverse times t. So this omega inverse and this omega would get cancelled, which means this is just going to give me g naught cos t. Okay, this is what this term is going to give me. And oops, and similarly, if you do the same exercise for the final term, which is mu times del, or this r prime times del r prime by r prime times del uz prime by del r prime, if you do this, you will basically get what, mu uc by r squared, because lc squared would come up, and you will get 1 upon r del r of r times del uz by del r. Okay, so this is going to be your third term. Okay, now if you just combine all the terms, you will basically get what? So on the left hand side, you will have rho times w uc times del uz by del t equal to g naught cos t plus mu uc by rc squared. Okay, and then you will have 1 by r del r of r times del uz by del r. Okay, so this you get when you substitute basically. So basically what you're doing is you are substituting this and this in the main governing equation, which is this. Okay, okay, all right, I hope things are clear. And then what I will do is I will write down uc, I'll write down uc as g naught r squared by mu. This is something that I will do, and let's do it. So then this becomes rho times omega, uc is g naught r squared by mu times del uz by del t, and g naught is just going to be g naught, and this is going to be cos t. Okay, and then this quantity is going to be once again what? So this is going to be, so uc is g naught r squared by mu. So then I'll write mu by r squared times g naught r squared by mu. Okay, and then I have this quantity, which is 1 upon r del del r of r times del uz by del r. Okay, that's it. That's so basically here I should write in one line. Okay, so what I can see from here is I can cancel G naught and G naught, and then this r square and this r square will get cancelled, this mu and this mu would get cancelled. Okay, so then I have a term which is rho times omega r squared by mu times del uz by del t equal to cos t plus 1 upon r del del r of r times del uz by del r. Okay, now here is the important thing. See, I know that this quantity is non-dimensional. This quantity is non-dimensional because I have written this in terms of all the non-dimensional variables. This is non-dimensional. And so is this quantity. This quantity is also non-dimensional. And this quantity is also non-dimensional. Which means that this quantity, rho omega r squared by mu, this has to be non-dimensional, right? That's only when the equality is getting fulfilled, okay? This has to be non-dimensional. And this is indeed non-dimensional because if you pay a little bit closer look, you can write this quantity as rho times r omega by mu. Now this r omega, you can call it as some, let's say, velocity v u omega, and then this quantity can be written as rho r u omega by mu. And if you pay a closer look, this is nothing but analogous to Reynolds number, and that's the reason why this quantity rho times r omega by mu, this quantity is sometimes known as the frequency dependent Reynolds number. Okay, so if I and I will call this rho times r omega by mu, I will call this as alpha squared because I know that this is just a non-dimensional quantity which is nothing but the frequency dependent Reynolds number, and then this equation just boils down to be alpha squared times del uz by del t equal to cos t plus 1 upon r del del r of r times del uz by del r. That's it. That is your non-dimensional equation for the corresponding dimensional equation that we that we had. Okay, where is alpha squared? As I said, this is known as the frequency dependent Reynolds number. Okay, so that's it. That's the non-dimensional. Maybe I'll write this as equation 2, and that's it. That's the non-dimensional governing equation. Okay, now there is one more advantage of why you are doing things non-dimensionally, because see, this is just a non-dimensional quantity, meaning I know that this is just order 1, this quantity is just also going to be order 1, and this quantity is also going to be order 1. Okay, that means I know that when you are doing things non-dimensionally, okay, and since I am saying that an order 1 quantity is going to be an order 1 quantity, I know that at least the velocity profile that I will get non-dimensionally, this is just going to be order 1. Okay, so I don't have to think about very large numbers. I also don't need to think about very small numbers, typically because I have used the correct scales in order to scale all the dimensional variables, which can be very large or which can be very small. Okay, and things, since I have already scaled them, I know that my non-dimensional variables are just going to be order 1. Okay, that's one more advantage. So there is one more highlight of solving things non-dimensionally, and an advantage which we don't get when we actually solve a dimensional equation. Okay, so that's it. Then the next part, and I hope the same equation you have derived when you were looking into the lecture series of this week, but the equation that you derived, that was dimensional, and this is the same equations which we have derived using a non-dimensional approach. Okay, now what we'll do is the next part is to solve equation 2 subject to the boundary conditions. So we'll look into the solution. So what we'll do is, as we have done, we will look into a solution of the form uz, and I know this is just a function of r and t now, And I'll say that the solution is of the form some real part of u hat of r e power it. And this is the solution form that we'll assume. We will throw light on why we are using this form of, why we are basically assuming this form of solution in the next class. But I would ask you to think about why you are, assuming. So basically, this is the solution form we shall assume. Okay, think about why we basically assume this kind of solution form in this given problem. Okay, I'll discuss more on this in the next meeting and in the next discussion hour, and we will finally find out the velocity profile, which is of course, see, the ultimate objective is to find out this velocity profile, right? That's the ultimate quest of this problem. And what we'll do is we'll substitute this into this equation, equivalently write down the boundary condition in terms of non-dimensional versions, and then we will solve for this uz as a function of rnt. And then finally what I'll do is I'll convert the non-dimensional equation into the dimensional equation and show you that this is the exact equation that you got in the lecture series when you are doing things, or when you're solving things in a dimensional manner. But at least you got the idea why we try to non-dimensionalize things, which I would say makes the analysis more rigorous, and at the same time more generic. That is something that I can say. Okay, all right. So if there are any questions, you can ask me. If not, we shall meet at the same time, as you know, using the same link next week, where I will discuss on how to basically, you know, so basically I'll start from why we are trying to assume this form of the equation. And remember, we in this question we also didn't choose an initial condition, although we had a transient term. And one of the reason why we didn't choose an initial condition actually boils down to the fact that we are choosing this form of the solution. Okay, and I will throw light on this in the next class. But yeah, this is from where we will start. Okay. Okay. If okay, all right then. If no questions, thank you very much for attending this session. As I say, please post your doubt in the discussion forum of the course. We will be very happy to address them. Till then, thank you very much. See you guys in the next class.